Hello, everyone. Welcome to 6.7 physical applications. I've been reviewing this a decent amount today, and man, this is a tough section. I'll say I've done a lot of math in my career to get my PhD, but I haven't done much physics, and it's been a while since I've looked at this physical stuff. So this is all to say, if this section feels tough for you, it was tough for me too. So maybe we can learn something together in this video. But the main thing I thought that was tough about this is because I'm not as familiar with force and work and how the units all interlap with each other. And there's a lot of just recalling of certain physics formulas that are just needed for a section like this that I know for myself I'm not as familiar with, but at the same time, I'm not even sure if some of y'all have taken a physics class. So this might be some new material for y'all in general. If it is completely new, that's totally okay. I would just say take these formulas I'm going to give you, or this review I'm going to give you at a face value. But if you have seen this stuff before, you might be a little bit of a leg ahead, but it's still good to review this stuff because they do interact with each other in a very like layered fashion here. So getting started with some physics review and formulas for and with calculus. For one, the main thing we're going to be talking about is force. Now, what is force? Uh, if you want to think of it as the Jedi stuff of just moving objects from one place to another, that's not totally bad. There's probably a good sketch there about Jedi masters talking about force to a physics professor. But in general, force is just the push or pull of objects, right? And the unit we use for force, because this guy was the guy that kind of first started discussing this, is newtons. We say n's for newtons. And if I have 25 newtons of force, that's like the measurement of force and the same as like meters and kilograms and mass and stuff like that. The main formula we have for force, this is where the magic happens, as one of my old professors of physics has said, is F equals ma. Force is equal to mass times acceleration. And what a newton is really just all this just like collection of units combined together in this way, because mass is in kilograms, acceleration is meters per second squared. It's like that second derivative of distance, right? And this is going to be one of our main formulas to break apart force when we're giving these physical application problems. So this is very important. Oftentimes, acceleration is just gravity, so that's something to keep in mind. On the other hand, work is the energy used when force moves an object a certain amount of distance. Now, we use these words kind of interchangeably in English, right? Like, oh, it took a lot of force to do this, or it took a lot of work to do this, right? But they do have some measurable difference in the language when regarding to the physical applications or physics in general. And work has its own formula as well. It's the energy used of force along a certain distance. So that's just measured through force as a vector. That's what this line on the top is there. Force is a vector along a certain distance. And the units we use for force or for work is going to be J for joules, a certain amount of force for a certain amount of distance, and this is meters. But normally force varies along distance. And a good example of that you can think of, for one, is springs, which I'm kind of getting ahead here. But imagine if you were like trying to move a box that's kind of close to a wall. So you like squeeze between the wall and the box, and you start pushing that box away from the wall. It might be tough to first push it because there's a little bit of leverage you need to get there. And also there's maybe friction on the ground and stuff like that. So it might be tough to initially start pushing it. But once you start pushing it and get more on a better leverage on the wall and a little bit more distance on the wall, so maybe you can push along the wall, then you can actually push even harder and have a different force at that distance through this entire simulation we're creating here. So force does vary depending on the distance you are at. And the way we would add that collection of forces together to create the amount of work we do is just adding certain small amounts of slices of this force, combining it together. That is exactly what an integral does. It adds a bunch of slices of things together to get a better, accurate assessment of what is going on. Another great example of this is for springs. There's actually a law for springs called Hooke's law for springs that says force is equal to K times X, where K is what we would call like a spring constant, and X is we'll say distance spring is away from equilibrium. Equilibrium. And you've probably felt this because you've played with springs before, right? You have a spring that's just in its like rest state. That's what we call the equilibrium point, the normal point the spring just is naturally at. If you compress that spring a little bit, it's probably not that tough to compress the spring at the very beginning. But the more and more you compress it, the tougher it gets because the spring just likes to fight back as it gets farther and farther away from that equilibrium point. So it requires more force the farther that distance from the equilibrium point is. It requires more force to push it in or extend it out in both ways. And it's actually just a very clean formula as well, because force is just some constant times that distance amount. And this constant, essentially, it determines how strong that spring is. The higher the constant, the tougher it is to push it in. Going a little bit on a different route here, there's a couple of other terms in the physics realm that's going to be important for these future problems. One is a relationship between mass and density. Particularly, density is equal to mass times volume, and we'll say, variables we use is a rho. It kind of looks like a P when I write it, but rho is going to be our density, V is our volume, and maybe A will be area and other problems as well. M is mass, also M is meters, so it hopefully be it'll be obvious in the context. And oftentimes our problems require us breaking down force more. So if F of is equal to ma or mg, if we're looking at gravity, we'll often use this formula as well to break down mass more because we know our density, we just need to figure out volume. And volume is a little bit more easier to work with in integral type problems, especially if we're looking at slices of volumes, right? Um, but there's a little bit of a augmentation we can make in certain types of problems with this relationship. In particular, if the object we're looking at is like a thin rod, a rope, a more linear or uniformly linear object, uh, then mass will just be your rho times like the length we go along that distance. Because we're now looking at things more one-dimensionally instead of three-dimensionally if we have some large object, right? Like the thinness changes the formula a little bit there. And usually, again, density also varies with length. If we have a long rod, but the rod has like different types of materials, maybe welded together, the densities of those materials would be different. So its mass would also be comprised, can also be found by making little slices along this rod, looking at the individual densities of each of these slices, making those slices really, really, really small, adding them all up. Oh, that's what an integral does. And that's how we get this formula as well. So all these problems we're going to be discussing in this part. I think I'm going to need to do another part as well because this is a pretty in-depth section and pretty dense. All the problems we're going to be doing is going to be using and combining a lot of these formulas in their respective constant contexts in a certain way so that we can get the answer that we desire. Now, this first one is going to be the easier of problems here. And because it's a spring problem, springs are usually easier to get a handle on. Okay. I never drink coffee, but here I am in this online class drinking a coffee. Um, So calculate the work required to stretch the following springs 0.04 meters from their equilibrium positions and assume Hooke's law is obeyed. One thing to make sure in like homework problems and stuff like that, always make sure you're working in meters. If you have a homework problem that has like 10 centimeters, that's really 0.1 meters, right? And if you start working in centimeters and just doing all the stuff you normally do, you're going to be a certain factor of 10 off because these formulas only work when you're working with the right units. So units in general are our friends. Make sure you keep track of them. So A spring that requires a force of 50 units to be stretched 0.1 meters from its equilibrium position. That just sounds like a mouthful. It's like, oh, how do we even figure this out? Well, what are we trying to find? We're trying to calculate the work. And when you calculate the work of something that has varying force, a spring has varying force depending on where you're pushing it from its equilibrium position, this is the formula we want to use. Work is the integral over a certain interval of the varying force. So for A, we know we want to do this because that's what work is along a certain distance. And we know it's a spring, so we know, I don't know my units integration, but I know my function is going to be some kx, where k is the spring constant. But I don't know what this k is yet. Now, this problem does give us enough information to figure this out, because it says a spring that requires a force of 50 newtons to be stretched 0.1 meters from its equilibrium position. This information can tell us what our k constant is, our spring constant is, because we have a point of reference now. If I know F is equal to kx, and I know when F is 50 newtons, the distance from equilibrium point is going to be 0.1 meters, then I can divide all this stuff around and stuff like that and get what k is equal to. Particularly, we're not going to care about the units here, but it would be k equals 500. So in this problem, k is equal to 500, which means we have the integral. We can find the bounds of the integration as well, because we know what the spring is. This tells us the information of what kind of spring it is and what our constant is. However, we want to stretch this spring 0.4 meters from its equilibrium position. So we're starting at equilibrium, and we are, let's maybe zoom in here a little, make this a little cleaner. We are starting at equilibrium, and we are stretching it by 0.4 meters, or contracting it by 0.4 meters, depending on how you view it. I think it says stretch, so either way, you're going to get the same answer. And our kappa, not our kappa, our constant is 500, x dx. And now we're just off to the races, right? We can just integrate, which gives us 500 x squared over 2, or 250 x squared, from 0 to 0.4. And that's going to give us, I have it written down here somewhere. Oh, actually, no, I don't. I just have plugging it in 0.4 squared. And you know what? I'll even get the number out too. Times. Oh, nice, easy number. This should be 40 joules because we are working with work. So not that bad. We started with this formula. We use Hooke's law, combined them together with the corresponding information, and that gave us the answer we're looking for. Let's see if I can shrink this a little bit so that I can make a little more room for part B. Like that. So for part B, we have a spring that requires 2 joules of work, can be stretched 0.1 meters, or to be stretched 0.1 meters from its equilibrium position. Now, again, the goal here is to find what our K is first. But either way, we're wanting to know work required from taking its equilibrium position and stretching it 0.4 meters. So it's going to be, this is what we're going to find. What does this information give us here? Well, it takes 2 joules of work to stretch from 1 meter of its equilibrium position in this different spring. A and B are different springs, right? And now this formula, which is really doing this formula again, but for the specific situation of stretching 0.1 meter instead of 0.4 meters, that's going to figure us out what our K is by simplifying this. So this becomes 2 is equal to kx squared over 2 from 0 to 1, or 0.1. If I plug in 0.1, I'm going to have 2 is equal to k 0.1 squared over 2, minus plugging in 0 as well, but we're going to ignore that. So it's going to be 4 over 0.1 squared equals k, or k equals 400. So that part B information found us what k is equal to. Same for the part A information for that. And now we can go through the process for figuring out what the work is when stretching at 0.4 meters. And we don't have to put the units here like that. So W is equal to integral 0.4 of 400 x dx. That's equal to 400x squared over 2 when you do the integral, or 200x squared from 0 to 0.4, which gives us 200.4 squared, which if I do this, 200 times 4, which should be 32 joules. These are our answers here for a problem like this. So hook saw problems usually aren't that tough. In general, the strategy is find the constant corresponding to your spring, which is this K value in these formulas. Plug it into your work because work is, or force is varying along the distance, which means work is going to be this integral here. And bing, bada, boom, you're going to find the answer. These next problems are going to be a little more involved, though. Oh, give me a second. Okay, so now we're going to go into a little bit more of an involved problem that doesn't have just a straight formula from the prior page, this first page here, on how to like use and figure out. But we're going to be combining some of this stuff together in order to like figure it out together. So the situation, we have a 20-meter long, 50-kilogram chain that hangs vertically from a cylinder attached to a winch. So I've written it out right here. We have some cylinder or building or something like that, some sort of winch on the top, and it's holding a chain. And a winch can like crank up a chain, right? And it's asked how much work is needed to wind the chain onto the winch. Now, first of all, we have to ask ourselves the question, is this a varying force? And in a sense, I would say no, because if you choose any of these points, the chain is just dangling from like the ceiling or something like that, or dangling from like the edge of a building, right? So the force that's being applied to it is just gravity, which force is m times a, but our a is going to be gravity, and gravity we should just know. I maybe should have put this in the first page here, but gravity is 9.8 meters per second squared. That's what we're going to use for all homework and stuff like that. So the chain is having just a constant force on it because the force is just what gravity is doing to it. However, the amount of work changes depending where we look at the chain, right? And we can think about it. Imagine if you had just, instead of it being a chain, imagine it being like a string with a ball, right? And the ball is where all the weight is, right? If I have a really small spring or string like this, to pull it to the top of the building, I just, lift it up a little bit and I'm good. But if I have a really long string and my center, my mass is all at the bottom of the string here, to pull that all the way up takes a lot more work than just, lifting it from this little itty bitty spring, right? So similarly, if I look at any points on this chain, the amount of work to pull this part of the chain all the way up is different than the amount of work to pull this part of the chain all the way up. So the work varies depending on the distance we are looking at, which means we're going to have to come up with a new formula or strategy based on what's going on here. So I'm going to say work varies depending on point of the chain. So what could the strategy be? The strategy could be to look at all of these points separately and individually look at how much work it is to move that point up all the way with the winch and the point below it all the way up with the winch and so on and so forth. And that looks a lot like creating an integral, having a whole bunch of separate pieces of work, adding it all together, combining it through an infinite fashion to create an integral. So strategy is going to be, instead of thinking of it as points, you got to think of it as slices. Slice chain into, I like saying, itty bitty pieces. Like so. So let's slice it like that. They're not in perfect displacement, but that's totally okay. And the intervals are small enough, we can treat it as the point we are wanting, and it has that point has a constant force. So I can say for a kth slice of chain, let me put a capital here. For a kth slice of the chain, work is going to be force times distance. And that distance might change depending on which slice you're in. So this distance is going to vary. But because my force is constant on this like small itty bitty slice, I'm not having an integral right there. It's just a force like that. And we know force is equal to mass times acceleration, or gravity here, times distance. And also, we don't know the mass of this itty bitty piece because the slice can maybe change depending on the slice can change the amount of mass depending on how big my slice is. So in order to get around that, I'm going to be now be using this relationship here, that mass is a density times volume, or in this situation, because we're working with a chain, which we can view as like a linear object here, mass is going to be density times the length we choose here. So if mass is equal to density times the length we choose, the length in calculus land, with using calculus notation, is going to be some change of y, this change of our slice here. So that's good. We want stuff like this if we're going to want to create an integral, right? And since density in general is total mass over total length, because it's a uniform chain, right? So the densities should be the same throughout. This is equal to the total mass is 50. The chain length is 20 meters. So 50 over 20, or 2.5 kilograms per meter. That's the density we're working at here. So combine that together, I have W is equal to rho times change of Y times G times a distance down from the chain, or W is equal to 2.5 times G is 9.8, so I'll put that in there as well, times change of Y times D. Those are the things we don't know so far. And the stuff I was concerned about in this problem was, oh, it takes different distance. The different distance determines the different amount of work it takes to move the chain up that much, right? So this is a problem here we need to investigate more. This is representing the distance a kth slice travels, or one of these slices travels. So let's write that out. The distance that the kth slice travels which is represented through this d variable, is equal to the distance to take the kth slice to the top. So I'll just say distance to the top. So if I had let's create some representative point in this slice here. Let's create some, this is the YK point, and the star means a representative point, we're going to say. That's like the standard notation I see. You don't have to really think of the notation wise, just think we're choosing a representative point here. If this is 0 meters at the bottom and 20 meters at the top, the distance to take this slice to here is 20 minus this distance, or this representative amount. So D is equal to 20 minus whatever that representative point's distance was here. So the work of the kth slice is W equals 2.5 times 9.8 times change of y times 20 minus y k star. That's going to end up being a y here. And if you simplify this, this becomes 24.5, and we combine the constants. And I'm going to put the change of y at the end. This is the work. Let's put this in blue here. This little slice right here, the work it takes to remove that kth slice is this expression. Now, if we want to add up all of these expressions together, make a whole bunch of these slices, maybe even limit it to infinity, that's where we end up getting an integral. So I'll say add it up slash limiting slices to infinity. This is going to give us the work. It's going to be, again, the chain is we're looking at distances from 0 to 20, so it's going to be integral from 0 to 20 here of this expression we have, but with dy's instead of change of y's. So 24.5, 20 minus y, dy. So we have set it up, right? I'm maybe even going to put this in green, because to me, this answer is more important. We did all of this work to set up to get to this answer here. And notice it took a lot of combining of formulas together. We started with F equals ma. We knew we had to look at each slice individually. So each slice has a constant force, which means we can use this formula. Combine the ma to mg because we're looking at gravity here. We expanded mass a little bit more as well. And we did this because we know the distance from the top of the winch to the slice we're looking at varies, which means we have to account that in our formula in some way here. That is the ticket. The one ticket is realizing the distance varies depending on the slice we look at. And the other ticket is realizing the slice that you're looking at has constant force among that slice if your slice is small enough. We're going to end up making smaller and smaller slices as we limit it to infinity, right? So we can take advantage of that, we'll say. But okay, let's finish this problem, because the integral is now the easiest part, right? This is 24.5, and the integral of something that's constant is just adding a y, and this is a y squared over 2 from 0 to 20. If you plug all that in and do a bunch of nonsense, you should get 4,900 joules. And again, I'll say this again, the key takeaway here, I know I'm probably going to go way over my hour mark in total among all these lecture videos, but the key takeaway is that on each slice of the chain, work is equal to force times distance, because force is constant. Force gets broken up into this. Mass gets broken up even further. And then we just interpreted all of these things together in the context of the problem to get an expression in terms of y. Once we have the expression in terms of y, integrate it, and you're good. Now, this problem is not easy. I would recommend you pausing and looking at this because we're going to do another problem that's very similar. In fact, it even has, I purposely made it as similar numbers, but it's it's still tough to see and figure out all the differences with it here. So let's look at this. This will be the last problem of this video. And it's going to be the star problem as well. So be sure to copy this one down and write the question associated to it too. So a 20-meter deep cylindrical tank of radius 5 is filled with water, to the brim, we'll say. How much work is needed to pump all the water off the top? And what changes if the tank is conical shaped? This is going to be your question you're going to need to answer. We'll get to that a little bit later. But again, let's draw this out here. We have a cylindrical tank, so it looks something like this, right? And it's filled to the brim with water. Should have used a thicker highlighter, but we're going to commit. And also feel free, you guys, to listen on like 2x speed if I'm going too slow, or slow it down if I'm going too fast for you. That's the beauty of online, right? It has a 20-meter depth. So let's do 20 meters here. Oh, let's start this to be at 0, and then this be at 20 meters. And it has a 5-meter radius. Now, how much work is needed to pump the water off the top? Well, again, similar to the chain problem, pumping deeper water requires more work. So we approach the same way. So how do we approach it before? We divided this tank, or this situation here, this picture, into itty-bitty intervals. Divide into itty-bitty intervals. And for the kth interval, work is equal to force times distance. It's going to be constant for that kth interval because you're small enough here. So catching up in this photo here, we have a bunch of itty-bitty intervals like so. Let's look at some kth interval like this, and we're going to get some slice like so. And this is the kth interval here. What is the work required to remove that slice of water to the top, or pump up that slice of water to the top? Well, again, force is equal to mass times acceleration. Again, what are we working against? We're working against gravity, so acceleration is just g, which is 9.8. Again, this is, in this example, mass, instead of in this case where we had a small chain, and chain, when it's a small uniform chain, mass is just like density times length. This is a large tank now, and the formula we have for something larger instead of something like a thin rod is mass is equal to density times volume. So that's the subtle difference between this, and you're going to see where that difference comes from, or how that difference changes the answer of our problem in this bit. So we have rho times volume in this case now. Okay, so plugging that in, rho times volume times g times d. And also, the density of water, we already know, is 1,000 kilograms per meters cubed. That's like by definition. So it's kind of like gravity. You're just supposed to know that. And your homework problems will give you those answers, because similarly, gravity is 9.8 meters per second squared. Okay, so if we're plugging in those numbers, we get 1,000 times 9.8 times volume times distance. And now the new, I guess, barrier we have for us is what is the volume of this slice here? Well, this volume can be seen as like a little bit of a cylinder. So what is the volume of that cylinder? Well, it's kind of like in volume of a box is length times width times height. It's like the bottom base times height. The bottom base is going to be a certain area times a height, right? Or the area is an area of a circle, so pi times 5 squared, since this radius is 5 here. And the height is going to be some change of y, because we have a change of y for the height, like that. Okay, so we have 1,000 times 9.8 times 25 pi times change of y times d. And again, just like in the previous problem, d has a certain distance we have to take into account. What is the distance of it takes for this slice to be removed, to be pumped out? Well, choose a representative point. Let's call this yk star for this kth slice, for the kth interval. The distance to take this slice to the top is this right here, or 20 minus this yk amount. So 1,000 times 9.8 times 25 pi times, I'm going to change d to be 20 minus yk star times change of y. Now, for the entire work, so work to pump the entire tank, is this. The integral from 0 to 20 again, because we're going from 0 to 20 here, and we're pumping the entire tank. So we found for a kth slice the amount of work to take that out. Have limit the amount of slices to infinity, add them all up. That's what an integral does, because integrals are really amazing. This is what, 9,800 times 25 pi times 20 minus y dy now. You change this to a dy for like that infinitesimally small amount. And again, I'll say, notice this is similar to prior problem setup. And I won't solve the integral, because you can probably do that on your own just by looking at the last problem. But again, getting to this point was the barrier, right? We should be at the stage to where integrating something like this is relatively easy for us, because we're just taking like antiderivative stuff from last class, or last course of Calc 1. But this setup, again, even if it had that same vibe as the prior problem, that was not easy to deduce and follow a direction for this. So the question that I want you to answer, since this is a star problem, is what if this tank was a cone instead? And this is an important problem because it's going to be on your homework. So instead we have, let's say, a cone like this, where we start with a radius of 5, like this. Well, the volume of each slice changes since radius is now changing. Now, I don't want you to go and resolve all this again, but say we're looking at some slice like right here now. Let me just create like something like this. So again, it's the same setup of the problem. We're trying to find the work it takes to remove all the water from this. At this slice right here, we have a certain radius. And let's say the entire distance is like 20, and then this is like some y here. So through similar triangles, I'll just say that's like my hint, similar triangles, you can figure out what the radius is right here in terms of y. What is radius in terms of y? And how does this change the setup of the integral? This is the real question I would want you to answer. Like this is the where this problem changes. So for any shape, if we're doing a similar problem, the way it changes is through this question right here. And essentially where it comes to is in here, when we were doing volume, our volume had a constant cross-sectional area because we're just having like cylinders and cylinders and cylinders. And here, our cylinders are getting bigger as we reach the top, which means our area of that base is going to be different, which means really instead of this being pi times 5 squares, it's pi r squared, where r is something in terms of y. So figuring out what that is what I want you to do for the star problem of this. And that is the end of part one, another long one. I'm going to do another smaller part, I think, for the second part of the physics application stuff. But yeah, this is definitely going to be tough. So please contact me if you do have any questions.